Okay, so in this video, we're going to finish 3.4. We are going to talk about maxes and mins now, relative extrema. So to get started, we're looking at that same graph that we started 2.4 with. And the question now, instead of talking about increasing and decreasing, we're looking at minimum and maximum values. So does this function have a minimum value? If so, at what point? So the minimum value for this function is -2. That's the lowest point this reaches, and it does that twice. And so yes, when y equals -2, that's the minimum. The points where that happens would be -2, -2, and positive 2, -2. Does this function have a maximum value? No. This doesn't reach a highest point anywhere because these keep going on forever and ever. So this is a no. Are there any points that are a minimum and maximum compared to the points around it? So these guys, these minimum ones, still work there. So yeah, -2, -2, and 2, -2. Those are min. And then there is a maximum that is a max compared to the things around it. It would be right here. It is a maximum if you just look like sort of zoom in on that window or that interval, and that is a maximum there. So yes, for a maximum at 0, 0. And that's called a local or a relative max or min. It's local, meaning that you zoom in on the point, or relative to the points around it. So it's not global or absolute. We'll talk about that in 3.5. But this is locally zooming in on a point, like regardless of whatever is happening elsewhere on the graph. Like this could go way down here, I don't know. Regardless of that, this is a minimum compared to the points that are right around it, relative to the points right around it. This is a maximum no matter what's happening up here. If I zoom in on this point, I have no idea what's going on over here. This looks like maximum. And so we're going to call it a local or a relative maximum. The derivative at those points is equal to 0. You can look at the tangent lines. What would be the tangent lines? They're all flat. So the derivative is 0. Okay, so then moving on to like a formal definition of the same thing. So f is a function defined at x equals c. So the function is not, doesn't have like a whole or discontinuity at x equals c. F of c is a local minimum if there exists some interval ab that contains c. So you're looking at some interval from a to b where c is in it, where f of c, I'm going to get that permanently there. You're looking at some interval AB, and there is some C value in there, such that f of C, so the y values around the y values at C, are the y value at C is less than the y values for the x everywhere else. So this is the lowest of those y values, and the rest of them are higher. So you have a local minimum, or that f of C is lower than the points around it. So this would be f of x, whatever. This is f of b up here. And then the opposite thing is happening for a maximum. You have some interval AB, you're zooming in on that interval. There's a point in that interval where the y value at that x value is bigger than all the other y values around it. And that's a local max. It's higher than the points around it. So this is A, B, this is C, so this is f of C, this is f of B, f of A. Okay, a function f is continuous on the interval AB containing C if it's continuous on the interval AB containing C, and f of C is a local max or min, then the derivative is 0. F prime of C equals 0, or the derivative does not exist. F prime of C does not exist. So that would be if f prime was 0, it would be like this. If it doesn't exist, it would be some sort of cusp like that. That doesn't look like a function. Let me redo that. Something like this. So you have that local maximum, and the derivative there wouldn't exist. Okay, these are very important points in determining maximas and minima. So we give them a name. Those are called critical values. Those values C in the domain of F, where f prime of C is 0 or f prime of C does not exist. What does the graph look like when the derivative is equal to 0? That would be like this, or like this, where the tangent line would be flat. When f prime doesn't exist, something like what we just did, this, or like this, where there would be a vertical tangent. That doesn't really get it. I didn't get that steep enough in there. Let's try that again. Oh, yeah, something like that, where that's terrible, where the tangent line would be vertical, so the slope would be undefined. Okay, vertical asymptotes and holes are not included in the list of critical values, and that's because they're not in the domain. So critical values are critical values of the function. So if the function is not even defined there, then it can't be a critical value for the function. Okay, so critical values again are going to be where we have maxes or mins, or the derivative is undefined. So this has a min here, local. It's also absolute. We'll talk about that next time. This is a local min or relative min at 2, -3. Here we have a local min. I was supposed to be listing critical values too. Sorry. I call those CV, critical values. The critical value here is x equals 2. Critical values here, again, would be where the derivative is 0 or undefined. So the derivative would be 0 here and here. So x equals -2 and x equals 1. That's not a local min, but this is. So we have a local min at 1, at -1. Okay. This one, we have critical values where the derivative is 0 at those two places, and here where the derivative would be undefined at x equals -2, -1, and +2. We have local mins at these two valleys. So -2, 4, and 2, 3. And they're local mins because, like, zooming in on them, it's the lowest point in that interval. Zooming in on this, it's the lowest point on that interval. That's why this one isn't, because even if you zoom in, like, this keeps going lower. It doesn't, like, go back up. Okay, and then we also have a local maximum right here where the derivative is undefined. That's at, I don't know, -1, 4.5 or something. Okay, and then this one, again, we're looking for where the derivative would be undefined or equal to 0 for the critical values. Derivative equals 0 or is undefined. Okay, critical values here, derivative 0. I don't have any place where the tangent line would be flat. And I also don't have any place where the derivative is undefined, because we're not going to include this vertical asymptote because it's not in the domain of F. So this has no critical values. Again, that's because vertical asymptotes are not included because they are not in the domain of F, so they're not going to be critical values of that function because they're not even values of that function. So, and this has no local extrema. No matter what interval you zoom in on, you're not going to find anything like here. There's points lower. There's nothing that like bottoms out or tops out even locally. Okay, so on the graphs above are the functions increasing or decreasing around the local maxima and around the local minima. So let's go back and look at that. So what's happening with the functions increasing and decreasing around the minimum? So around this minimum, we're decreasing in and increasing away. This one too, decreasing in, increasing away, decreasing in, increasing away, decreasing in, increasing away. What about local maxes? We only have that one. Don't use purple, use blue, use purple. We're increasing into and decreasing away from the local max. So on these graphs above, for the local mins, we are local mins decreasing into and increasing away. And then for the local max, we are increasing into the maximum and decreasing away. Okay, so we're going to sort of solidify that as like a process. So find the intervals of increasing and decreasing. This was 3.4a. We did this in that last video. So find the critical values and the values not in the domain, plug them on a number line, plug in test values. If it's positive, that's the increasing. If negative, decreasing, because you're looking at the slope of the function. So this is what we did. This is our like f prime number line that has the critical values on it. So to determine if it's a max or a min at those things, you are doing what is called the first derivative test. You're looking at that first derivative. So if you have something like this, who knows, you have plus, minus, plus after you do this, right? So this is increasing into the point, decreasing away. This is decreasing into it and increasing away. So this would be a maximum and this would be a minimum. Decreasing into, increasing away, increasing into, decreasing away. If it switches from increasing to decreasing, then it's a local max. If it switches from decreasing to increasing, then there's a local min. And you can see that if you just sort of like connect those arrows, right? So let's do that with the some of these examples. Local extrema happen at critical values. So if it's not in the domain, it's not. So asymptotes and holes won't matter. So let's do this. Let's do what we were doing before. We're trying to find a critical value. So f prime of x would be 9 minus 2x. This is defined everywhere, so we don't have any places where the derivative is undefined. So then we're going to set the derivative equal to 0. So x equals 9/2. That's going to be our critical value. And we're going to put that on a number line, just like we did before, 3.4a. So f prime, we're putting 9/2 on here. 9/2 is, what, 4.5? So what if we plugged in 5? Let me do some different color. What if we plugged in like 5 over here and 1 here? So f prime of 1 would be 9 minus 2 times 1, which is 9 minus 2, which is 7. So that's positive. And f prime of 5 is 9 minus 2 times 5, which would be 9 minus 10, which would be negative 1. So that's less than 0, so that goes here. So we're increasing into 9/2 and decreasing away. Increasing into, decreasing away. That's going to be a local maximum. Uh, 9/2, and then we need to figure out what that y value is. This is f, go back to f of 9/2. So f of 9/2 is 9 times 9/2 minus 9/2 squared, gross. But 81 over 2 minus 81 over 4. So that's going to be 81 over 4. Okay, so then this tells us that our, oh my goodness. This tells us our, that's really hard to see. Let me see. Let's see. That's going to be worse. Pink? Yeah, that's good. This tells us our y coordinate for that ordered pair, which is going to be 81 over 4. Okay, so we did this process, right? Find critical values and values not in the domain, plot them on a number line, plug in test values into the derivative, increasing, decreasing. If you wanted to give those intervals, this is increasing from negative infinity to 9/2 and decreasing from 9/2 to infinity. Again, that's based on that number line, that f prime number line. All right, let's keep going with some more examples. So we're going to do all these. We're going to do increasing and decreasing intervals too here just for practice. So taking the derivative, f prime of x is going to be here, put that 2 down front. Then we make that 1. So this is just x minus 4. 2 times 1/2 is 1. X to the first minus 4 times x to the 0 plus 0. Good. This is defined everywhere. So we are going to move next to doing setting this equal to 0. X minus 4, so 4 equals x. This is our critical value. So we're going to plot our f prime number line, put this on there, and then plug in some test points, maybe 0 and 5. So f prime of 0 would be 0 minus 4, which is negative 4, so that's less than 0. And f prime of 5 would be 5 minus 4, which is positive. So we are decreasing into the point and increasing away. So that is going to be a local min. You can sort of connect those arrows and look at that. That's a local min. When x is 4, we need to figure out what that y value is. This y value is f of 4, not f prime, but f. So that's 1/2 4 squared minus 4 times 4 plus 3. 1/2 4 squared 16, that's 8 minus 16 plus 3. So that's negative 8. Negative 8 plus 3 is 11. Negative 8 plus 3 is negative 5. So that is our local minimum. And again, just so we can do this all together, increasing and decreasing, where the derivative is positive is our increasing interval, so 4 to infinity. And where the derivative is negative is our decreasing interval, so negative infinity to 4. All right. Number 3, f prime of x is 3x squared minus 4x plus 1. That's 3 power rules. Exponent down front, decrease it by 1. Exponent down front, decrease it by 1. That should be a plus sign. I don't know why I made it minus. So 3x squared plus 4x plus 1. Okay. This is defined everywhere, so we don't have to worry about discontinuities, but we will set it equal to 0. So we're looking at this quadratic, which we can factor, or you can do the quadratic formula for, whichever makes sense to you. I am a guess and checker personally for factoring, so I would do something like this. I need numbers that add to give me, that multiply to give me 1, so these should both be 1, and multiply to give me 1, add to give me 4, so these are both going to be positive. That would be, if I were to FOIL this, that would be 3x squared first, outer would be 3x, inner is x together, that's 4x, and then left would be 1. Okay, so that works. And then set those factors equal to 0. So 3x plus 1 equals 0, x plus 1 equals 0, so x equals -1, and x equals -1/3. These are your critical values. So we're going to put those on a number line. It is an f prime number line with -1 and -1/3 on it. We are going to put some test values on here. These are going to be trickier. So -2, maybe 0. In here, maybe -2/3. And then test those points. F prime of those things. So 3 times -2 plus 4 times -2 plus 1, that's -6 minus 8. So this is going to be -6 minus 8 is -14 plus 1, -13 or something. It's negative. Uh-oh. -6. Oh man. I plug it into the right thing? Yes. -6 minus 8 plus 1. That's negative. I believe that that's negative. Do y'all agree with me? That doesn't match my own work, which is a problem. Okay, so 2/3 times 3. Oh, that's squared. Oh, why don't I have this worked out? Hold on, let me work this out with pen and paper. 3x plus 1, 2x plus 1, times -2 plus 1, -2 plus 1. That's -6 plus 1, and -1. Okay, so I have positive for that. Oh, because that's squared. This is the problem. That's squared. Okay, I knew what we get there. That's 4. 3 times 4 is 12 minus 8 plus 1. That is going to be positive. And then if we plug in -2/3, we have 3 times -2/3 squared plus 4 times -2/3. Y'all use a calculator. Don't trust me, but this is going to be less than 0. And then if you plug in 0, you could have 3 times 0 squared plus 4 times 0 plus 1. That would be positive. So increasing, decreasing, and then increasing again. So you can sort of see a maximum happen here and a minimum happen here. So we have a local max at -1 something and a local min at -1/3 something. We'll figure that out in a second. This is increasing from -infinity to -1, and then also from -1/3 to infinity, and decreasing from -1 to -1/3. And then for these guys, f of -1, plugging that all the way back into the first, to the f. So -1 cubed is -1 plus 2 times 1 squared plus 2 minus 1 minus 2. -2. And then f of -1/3. Use your calculators. -58 over 27. Okay, so there are your local max, local min, your increasing and decreasing intervals. And that's the first derivative test. Let's see. Let's do this one last problem. We have, and then you guys can practice those other ones. So f prime would be ho d high, so bottom times the derivative of the top, minus high d ho all over ho ho. So this is undefined at 0. So that's going to go on our number line. What else is going on? Let's simplify the top. We have 2x squared minus, let's do that one. 2x squared minus x squared plus 16. Make sure to distribute that minus sign over x squared. So that would be actually just x squared plus 16 over x squared. Okay. So then we are going to, you didn't have to do the quotient rule there. You could simplify this, right? And then do the power rule twice, but whatever. So we want to know where this is equal to 0, that would be undefined. We have that. Where this is equal to 0, the whole thing would be equal to 0. So we're going to set this top part equal to 0, and it never is. Right? X squared plus 16 can't equal 0. That's not a thing because you have x squared equals a negative number. So we only have that one thing to put on our number line. We only have x equals 0 to put on our number line, the place where the function is undefined, where f prime is undefined. So if we picked test values for that, what color are we doing that in? Blue still. Hold on. So our test values, say we plug in -1 and 1. When you do that, you're going to get both positives. F prime of -1 is -1 squared plus 16 over -1 squared, so that's positive. And f prime of 1 is going to give you the same thing because of those squares, which is also positive. So this is actually increasing everywhere except for at 0. So this is increasing from -infinity to 0, and then from 0 to infinity. And there are no local extrema. It's increasing the whole time, so there's no place where we could have an sorry, it's increasing the whole time, so there's no place where we could have an extreme happen. Okay, so I want you guys to practice these. This is increasing and decreasing intervals, which we just went through in those examples too. If you need to see any of this worked out, just email me and let me know. Thank you so much.